So the third lecture in this chapter is on balancing oxidation and reduction reactions. This method works for any type of reaction. So the method you learned back last year was what's called guess and check, which, you got a reaction and let's back this up. You got a reaction like, let's say, lead chloride reacting with tin bromide, and you would switch and do your double displacement, and then you'd get your bromide and your tin chloride, and then you try to balance it and say, okay, well, I got 2 chlorines on the left side, so I'm going to need a 2 here. Now that balances. Now I'm going to need a 2 there. And so you would just keep going back and forth until it balances. That's called guess and check. That does not work on really complex reactions. So the oxidation reduction method works for anything. So first way is we're going to define oxidation numbers. And the way I would define oxidation numbers is made up way of keeping track of where electrons are going in a reaction. Okay? A charge, on the other hand, is not made up. When you've got a charge, it means that the ion has truly lost or gained electrons. So charges, you put the number and then the sign. Whereas oxidation numbers, you put the sign and then the number. So when you were taking chemistry, we really didn't make too much of a distinction of this, but a charge is the number first, then the sign. Whereas an oxidation number is the sign first, then the number. So now in AP Chem, this is going to make a big distinction. So you have to start doing it correctly. Okay? So again, oxidation numbers are a made-up way of keeping track of where the electrons are. So you're probably saying to yourself, okay, if this is made up, why am I studying it? I'll just give you a little story here, or an analogy. So when I was in high school, as it still is, gambling is not allowed in school. So my friends and I, during lunchtime, we would play cards for money. But we couldn't play cards for money because gambling wasn't allowed in school. So what we did instead was we played for points. So as we played cards, by the end of the lunch hour, I might be up 4 points, and my friend might be down 2 points, and somebody else might be up 7 points, and someone else might be at 0 points. And a point was equal to 25 cents. So if I was up 4 points, then later on Friday night outside of school, we would settle up our money. So it's kind of like that. The oxidation numbers are telling us where the electrons are moving to, even though those things don't actually have that charge. Okay, only charges really exist. So let's go through the rules for oxidation and reduction. Okay, so first we have to be able to assign the oxidation numbers. Okay, and on page 171 in your book are all the rules. So the first rule is all elements have an oxidation of 0. Okay, so if you have gold in its most common form, its oxidation number is 0. Okay, hydrogen in its most common form, oxidation number 0. Okay, not H, because hydrogen most commonly is diatomic, H+. So H2, the diatomic form, is 0. Okay. Rule number 2, for monatomic ions, their oxidation is the same as their charge. For monatomic. So if sodium has a 1+ charge, it would then mean that sodium would have a +1 oxidation. Okay? Or in the case of aluminum, if aluminum had a 3+ charge, it would have a +3 oxidation. Okay? Rule number 3 talks about fluorine. Fluorine has a -1 charge. Not as important rule. Rule number 4, oxygen has an oxidation of -2. Okay? Except when it isn't, and I'll get into those exceptions at a much later date. I don't want to get them into the exception too early. I don't want to talk about peroxides, even though the book does, because it'll just confuse you. So the oxidation number of oxygen is -2, and then the oxidation number of hydrogen ion is +1. So now if you're saying to yourself, this looks a lot like these things are just charges. Well, it does look that way, but let's do an example and it'll make a little bit more sense to you. So let's suppose we want to assign the oxidation numbers to, let's say, hold on here, come on back. There we go. Let's say potassium phosphate, okay? So potassium has a +1 charge, and they said that monatomic ions have the same oxidation as their charge. So then I would go back and I would erase this and I would write +1, okay? Sorry, I didn't balance that. There's a 3 there. Now, this entire phosphate has a charge of 3-, okay? So that phosphate definitely has a -3 charge, but that -3 charge is spread over the phosphate and the 4 oxygens. It's not like the -3 belongs to the phosphorus or the -3 belongs to the oxygen. It's spread over all 5 of those atoms. So the oxidation numbers inside the parentheses has to add up to the overall charge. So I'm going to use a different color here. I'm going to stay consistent. I'm going to put my oxidations in green. Okay? So oxygen always has an oxidation number of -2. 2 times 4 is -8. And then whatever the oxidation on phosphorus is, it must add up to -3, the charge. So the oxidations inside the parentheses has to add up to the charge outside the parentheses. So what would that be? Well, it would have to be +5, okay? Now this is where I I'm going to show you that these oxidation numbers are made up. So if we do the Lewis dot structure, here's phosphorus, okay? Here are my 4 oxygens, okay? Because it has a -3 charge, it means there's 3 extra electrons that I got from somewhere else, okay? So the fact that phosphorus has a +5 oxidation does not mean there is a +5 charge on the phosphorus. It means that the phosphorus is behaving as if it's got a +5 charge, okay? And the oxygen with a -2 oxidation is behaving as if it had a -2 charge. But it doesn't really have a -2 charge on it. Okay? If we look at the electronegativities, oxygen is a 3.50 and phosphorus is a 2.06. Okay? What that means is the oxygen is stronger than the phosphorus, and therefore the electron density is being pulled towards the oxygens. So the electrons spend most of their time around the oxygens and very little time around the phosphorus. And therefore, phosphorus behaves as if it has a +5 charge, even though it really doesn't. And the oxygens behave as if they had a -2 charge, even though they really don't. So, and if we truly drew this Lewis dot correctly, all electrons look the same. So you wouldn't know where the extra electrons actually are because they're being shared by everybody. All you know is this entire thing has got a 3- charge, and that the oxygens are behaving as if they're -2 and the phosphorus is behaving as if it's +5. Okay? So that's how that one goes. I think I'm going to stop here and do another lecture tomorrow. I think this is probably as deep as we want to go at this point.